Welcome to another instructional video from OWL, the wise choice in fiber optic test equipment. I'm Professor Jim Powers.
Patch cables and test equipment should always be checked prior to testing to ensure accurate and reliable test results. Usually the best time to do this is at the beginning of the testing day. In this procedure, we will be using the Fiber-OWL 4-volt optical power meter and the Laser-OWL single-mode light source. You'll see there are 3 patch cables and 1 mating sleeve that we will use in this procedure. Okay, you'll see these 2 cables here. They will be plugging the Laser-OWL into the link under test. Now, there are 2 cables here because there are 2 wavelengths that we will be using for testing. Okay, it's easier to handle a duplex cable than 2 simplex cables, so it's better to have a duplex cable for this. This 3rd cable will be used to connect the Fiber-OWL into the link under test. And this mating sleeve will be used to, for this procedure only, just to check that this patch cable is okay. One thing you need to make sure though is make sure that the connector types on your patch cables are correct. And that they match the test that you will be doing. On one end of the cables, you need to make sure that they plug into the testers themselves, in this case SC. And then the other end of the patch cable will be plugging into the network. So this could be any connector type. In this procedure, what we'll do is we'll just demonstrate using SC. We'll just assume everything across the board is SC. Now, the first thing we need to do is turn the units on. Just press the power button on each. Okay, notice that the Laser-OWL powers up to the 1310 nanometer wavelength by default. And the Fiber-OWL, once it finishes booting up, will show a couple different test options. One of which is Simple Meter. Simple Meter is what we will be using for this demonstration. So it's already highlighted on Simple Meter. We just press F2 to select. Okay, notice that on the screen here it says 850 nanometers. Okay, this is a multi-mode wavelength. We can't use this wavelength to test our single mode. We need to press F3 for wave until we see 1310 nanometers. Okay, so now both the meter and the source match at 1310 nanometers. Okay, you'll see that the reading on the screen says under. Okay, what this means is that there's no light coming into the detector. In fact, if you look at the top of the Fiber-OWL, you'll see that it says detector right here. This is where the measurements are taken. Okay, this light source over here is only used for length measurement. We won't be using it for this procedure. Now, if we take this dust cap off, you'll see that now there's a reading on the screen. But what this reading is just room light, ambient room light coming in from the ceiling lights here. Okay, this is what power meters do. They measure room light. So whenever you disconnect, you'll see a reading similar to this. So we connect our duplex patch cable in next because we want to check to make sure that these cables are okay. So we plug one into the 1310 port. And we plug the other one into the 1550 port. Okay. Then we take our reference cable and we plug it into the detector port here. Okay, notice that we have a reading here of around minus 10.46. Okay. Now, is this good? By all means, this is good. Our target value for single mode light sources is minus 10. Okay, it could be a little higher, a little lower. In this case, it's a little lower, but this is an acceptable cable. Okay, now what we want to do is, actually, let me go back. Really, we want to make sure that we're not lower than minus 11 dBm. If we're below that, then there might be something else wrong with the cable, and it shouldn't be used for testing. So once we've checked our 1310 cable, we need to check our 1550 cable. Okay, again, see, it goes down to a ambient room light level. We plug the 1550 cable in. We'll see that it goes to under again, okay, which means that no light's coming in, simply because we haven't switched any of the testers to 1550 nanometers, which we will do now. Just press the lambda button on the Laser-OWL, and then the F3 for wave, until we see 1550 nanometers. Okay, here we see minus 10.07. This is very close. Remember, we want to be a little higher, a little lower. We're just a little bit lower here, and we're above minus 11 dBm. So this 1550 nanometer cable is also fine. But now we need to check this third cable. The easiest way to do this is to temporarily zero out this 1550 nanometer wavelength. What we'll do is we either press F2 or the 0 key here, and that will do the same thing. It'll set a reference for this wavelength. So we press F2, and it'll say set 1550 reference. We press F1 to confirm, and you'll see that the reading changes to 0 dB now. It's not in dBm mode anymore. Okay, this is the reason we call things zeroing. Now, to connect this straight cable in, or this power meter cable, we plug in this mating sleeve to the reference cable. We plug the other end of the mating sleeve into the test cable for the fiber owl, and then we plug the other end of this reference cable, or this test cable, into the detector port. Okay, notice we have a reading here of about minus 0.1. Okay, what this means is that by adding this third cable and this mating sleeve, we are introducing an additional, a tenth of a dB of loss. Okay, now this is actually fine. We expect to have a little bit of loss here. Okay, really what we want to do is make sure that we're not exceeding around 0.4, 0.5 dB by adding this straight cable, or this third cable in. Reason being is that this cable is unknown. We won't know exactly what this loss is, and it actually is not being zeroed out during the test procedure. So we need to check this cable, and we see that it is actually a very good reference or a test cable to use for the fiber owl. So now that we've checked all of our equipment and accessories, we can go on with our test.
If the power level falls below the acceptable power level range, debris such as dust, dirt, or finger oil may have collected on the connector end face or in the equipment's optical ports. Thoroughly clean and inspect all connector end faces and equipment's optical ports according to industry standard cleaning procedures. Several cleaning cycles may be required. Keeping connectors and optical ports clean at all times helps to keep test equipment in good working order and proper calibration, ensuring accurate and reliable test results. When not in use, dust caps should be kept on fiber connectors and optical ports to keep debris from collecting on the surfaces of the connectors and ports. During testing, it is highly recommended to clean and inspect both connectors and optical ports every time a connection is made. Failure to properly maintain your test equipment could needlessly result in costly repairs. For example, over time, repeated connector insertions into a dirty optical port could grind the debris into the optics in an equipment port. This type of damage is permanent and cannot be repaired in the field. If the problem still exists after thorough cleaning and inspection, the patch cable may need to be replaced. Patch cables are typically rated for a few hundred connector insertions, but can prematurely wear out or become damaged if they are not properly handled and maintained. If the power level is still too low, even after patch cable replacement, contact OWL Technical Support for assistance. This has been another instructional video from OWL, the wise choice in fiber optic test equipment. For more information about additional instructional videos or OWL fiber optic test equipment in general, please visit OWL's website at owl-inc.com. I'm Professor Jim Powers. Thanks for watching.